Okay, right. There's a beam, total length 8 meters. Okay. Whenever I see the two elements, they look similar, I don't need to write two stiffness matrix. I'll just use this one. So in this case, the whole beam is uniform across and has the same area. So this K and that K is the same. The K value is a 2 gigapascal times 4 times 10 to the negative 4 meter cube over the length cube, which is 5, exponent 5. Okay, and now let's assemble the local stiffness matrix. This too is local. Okay, according to the notes that we have in beam elements, okay, remember that beam elements note we had? $12 and then 6 times length, which is 4, right? And then 12, negative 12, and then 6 times 10 to 6 times 4. 6 times length, 4 times length square, negative 6, 4, 2 times L square, oh, which is 4. So, any questions so far up to this step?
This one is question 4 from the problem set, not the bonus.
That's right. There's only the first picture I sent you. It's not a bonus yet. The bonus, I'm going to show you how to join the beam elements with the spring element.
Why is the L cubed? K equals EI over L cubed. I thought it was EI over L.
EI over L never exists. For spring elements, it is EA over L. Okay. For beam element, is EI over L cube. In all exam and midterms, I will provide you a formula sheet so you can go look at it. You don't have to flip through your notes anymore. You just look at the formula sheet. It's good enough.
What happens if K1 is not the same as K2?
And you cannot share the same constant.
Can you upload that formula sheet that you said so we can work off of that with the practice questions as well?
The formula sheet with it's right here. That's the formula sheet. It's given. right? You talking about this formula sheet?
No, I thought you said you were gonna like provide us with the sheet for the test or something.
During your test, yes.
Yeah, so whatever that sheet is, could you give it to us so we could practice using that sheet with other questions?
Oh, you mean beforehand, before a
Mhm.
midterm? Yeah, I can do that. Yeah, yeah. Anyways, this is the local matrix for the beam elements. Now let's look at, well, because the force is funny, right? Force is funny for the beam element. So I got to find a way to deal with force as well. The force, 1 equal to force 2 as well, the same force, right? It's a 5,000 Newton per meter all across. And then what is the force factor in this case? It's pressure times length over 2. And then the second term is the pressure times length square over 12. So if my apologies, I'm taking a lot of sneeze break today. Okay, let's use them. It's pressure times length over 2. Length is 4 over 2. And I need to reach 5,000 times square over 2. I'm not going to write down a lot, okay? I'll reuse that term and also so now we have 2 local matrix and 2 local force vector. Now let's assemble them together.
Sir, I have a question.
Okay, what is it?
I know the unit of the pressure is Newton over meter square, but like here it's a Newton over meter.
That is the pressure over a line, the linear pressure. In this case, yeah, in this example, the beam element is only a linear pressure along the line. You're right. In the beam elements, we only deal with a linear pressure over the line. It's not actually a pressure over an area. Okay. Good point. So in this very special case, we only deal with the linear pressure along the line. It's not really a pressure over an area.
Okay.
Okay. Okay, so we assemble both matrix together. Let's deal with the local factor first. Now, the second vector is Please note this one, this term, and this term is the same, which is because we have a very similar element, actually identical element. So we just repeat that. Okay. Okay. We assemble both matrix together. Which is 24, -12, and then 24. Two times 16 is 32. Okay, I need more space to write. I'm gonna erase that. Okay, now we rewrite another term, right? So just right here, time plus 64, okay, plus 24. Okay, and everything else is 0. Okay, I'm not gonna spend time writing it all. Okay, just pay attention though. Be careful when you add those terms. Okay. And finally, we define the displacement vector. Nook 1's allowed to move up and down. So we define V1, and then it is allowed to turn as well. Nook 2, same thing. It can move up and down, and it can turn as well. Nook 3 is up and down. It's allowed to turn as well. And we know Nook 1 is attached to the wall. So it's not allowed to move up and down. It's not able to move, turn as well. Same as Nook 3. Okay. So on the right side, it has a reaction force holding the beam member together, and also is fixed with the angle. Same thing as a Nook 3. Because this is 0, when you multiply them together. Okay. Okay, let's focus on these two equations only. Row 3 and 4. Because it will get me an answer right away. Okay. So on the row 3, we get 20,000. This is 0. Row 4 is row 4. This is 12 plus 12, 24 V2. And then 0 times 5, 2, which is 0. Nothing at all. Okay. Oh my goodness. I made a mistake here. What did I miss? Very important. K value, okay? Right here, V2 times hold on a second. Yep, V2 times 0, which is nothing, and then plus 64 plus 64, 128, 2. And right here, we got nothing. So we know it's not turning anywhere. Angles, the middle point is not turning anywhere. And then V2, we can solve it by this divided by 24, which is
So
You
don't
need
you
the
need to
K
multiply
value
the
for
K
the
value? Yeah.
Yeah, the 24 will be multiplied by the K, no?
sorry guys, I'm very sick today. I suck. Yeah. Okay, by the way, guys, I want to show you something though. You know, we can resolve that in a faster way. You know how time consuming it is to merge two matrices together, but we can simply just work on one element only. When we have a beam and we know both sides are identical, okay, I can just apply a symmetric line. To it. So what is the condition? Okay, we know V1 not moving, psi1 is also not moving. However, right here, we have V2, we know it's going to drop when you have a pressure on top. And because left and right are the same, right? So we know theta2 will not be turning because it's sagging in the same direction. So how do I deal with that? Okay, we rewrite the whole thing. I'm missing a 0 there. And it is 12, 24 minus 12, 4. Okay, instead of dealing with two elements, oh, what did I miss? Big deal. Do not forget this, guys. This is big deal. Okay, in this case, what do we have? Okay, we apply the boundary conditions. V1 and psi1 is 0. And we we apply the boundary condition on the middle one, the symmetric boundary conditions. Psi 2 is also 0. On the left side, F1, we have a reaction force and we have a reaction moment as well. So we times this vector to matrix, and we know right away if I have a unknown here, so I'm focusing on row 3 only. Okay. We have 10,000 times K V2 times 12 V2. What do we have? V2 is same as what we did before. Any questions so far?
Is K 10 to the minus 6 or 10 to the minus 4? I think previously you wrote, yeah, 10 to
K
the
is
negative 6.
K is a 1.2 exponent 5.
So then the V2, see how you have a negative 6.6667 times 10 to the minus 4? In the previous one, it says 10 to the power negative 6. Oh, sorry, it's 4. Yeah, I thought it was 6. I'm sorry.
Hey, don't worry, man. You know what? It's a good idea. Try to work, forget about what I wrote here, because I just did it in a rush time and I'm not feeling all right, right? Try to rework the problem set on your own, okay, without looking at my answers. Okay, you will feel better this way. And also, whenever there's a case with whenever there's a symmetric case, work on one side only. Okay, it's gonna work. You know, why work on two? Because it takes so much longer to deal with a 6x6 matrix instead of a 4x4, right? Okay, I send you two parts of the question, which is the regular one and the bonus one. The regular one. Somehow it is attached with a new column, right? So how did we deal with that? Okay, don't panic. We know this stiffness matrix already. We have the K. And we have the force. Let's call that matrix B. It's a beam element, right? And we have a matrix of a force beam. This is just a spring element, right? So we have a stiffness matrix for the beam, for the spring, and also we have a force vector for the spring. We have the stiffness matrix for the beam already. We have a force matrix for the beam as well. And we're going to calculate the stiffness matrix for the K. Spring element matrix is so easy, which is, okay, by the way, the EA E A over L is, according to the question, is 4 times 10 to the 6 Newton per meter. So it's going to be,
And that'd be using, oh, never mind.
okay, but check this out. We are working on, we want to take a shortcut. So we deal with half of the beam only. So this is a full beam, right? So we want to deal with the half of it because it's a symmetric problem, okay? Any problem? Questions? Okay, I'm going to carry on. So on, okay, by the way, before I join them together, I want to define the displacement vector, global displacement vector. I use this to guide me, okay, to assemble them together. What components do we have for the global displacement? We must have V1, phi 1. Right here, we have V2, 2. What else do we look at? The spring element is attaching to a third node, V3. Does that thing have a phi? No, because the spring elements doesn't turn, so we don't have a V3. The global displacement vector will be V1, phi 1, V2, phi 2, and then V3. So we know it's going to be a 5 by 5 matrix. Okay. Okay, lots of copy. We copy the same terms, 12, 24, 12. Oh, December, remember. Okay. 24, 24, 64. Oh, sorry, guys. Mistake. 24, 32, negative 24, and then 64. Okay. So how do we this to inside? Okay. Okay, because there's a scale factor here, I must divide this by this scale factor first before adding inside. So it's 2e6 over k. Same here, right here is a negative 2e6 k. 2e6 over k. Do you understand what I'm doing here? Okay, I cannot just write, oh, 2e6. No, because there's a scale factor here. I must take care of this. Right here. On the left side, the force vector is 10,000, negative 6,667.
The new matrix that you get for that column, shouldn't it add to where the 12 is? So it's like with the V2 and V3, or do you want it to work for the angle too? Like when you're adding them into the other matrix, do they all add in beside each other like that?
Oh my goodness, sorry man, you're good. Let's see. My fault. Okay, good point. I'm so sorry. Yeah. You're right, because the stiffness matrix for the spring element looks after V2 and V3. It's so wrong to add the values to 64. Okay, you should deal with the same notes. Okay, they only add together when they have a common degrees of freedom. In this case, V2 on the spring elements and phi2 doesn't have the same degrees of freedom. Only V2 and V2. Thank you for correcting me, you know. Then what? What's the next step? Okay, we deal with the F3 is a reaction or force free. And we have a, okay, again, same mistake. No, hold on. This is right, yeah. Okay, better? Okay, what's the next step? We define the boundary conditions. V1 is not moving, phi1 is not moving, and then also it is, the column is steady at the bottom of the floor, okay? Due to symmetric problem, phi2 is 0. Okay, so after all, a 5x5 matrix is not so scary at all because we have 4 zeros. So it's down to 1 row only this row. We multiply the force vector to the matrix. K times V1 times 12 plus, why did I do this? 6 over K. Yeah. Another typo. FGA is all about attention to details. And then we know K is a 12.5 times 10 to the 5th. So we can solve for it, okay? E2 is whatever it is. Any questions on this?
You still have to solve for your forces, right?
if I ask for it in the questions, yes, you solve for the
Okay.
forces. But in the question, I only ask for deflection, right? So who cares about forces, right? In your midterm, right? Solving the matrix only worth probably 10-15% of the total score. Okay. I would say if I give you 4 problems, 4 questions, you work up to here, okay, and then you can solve it later on. Once you're up to here, you get at least 80% of the total score already. You know, do not spend time dragging on one deflection or force vector. Like, also, if I don't ask for the force vector, who cares? You know, just work on deflection only. Okay, save instead of working on 5 equations, you work on you deal with 2 rows only. So much faster. I want to ask you a question. Say, did you guys try this quiz 4? I just posted. Any chat?
No, I haven't tried it yet.
Okay, how about this? Let's take a short break for now because I really need to blow my nose. Okay, sorry about it. Okay, let's come back at what time is it? 10:15. Okay, I will briefly show you how to deal with this problem. Okay, so you, I'm not gonna do the whole thing for you because you still need to work on a quiz 4, but I'll at least resolve half of it and you can carry on because I expect you to know a similar problem like that in your midterm exam. Is that cool? Okay, let's reconvene at 10:15. Thank you. Let's take a short break.